Hi, Chuck McCown here. We're talking today about our POE products, the GigE POE, both surge suppressor and power inserter. This comes in two different versions. The APC version is named APC because it fits really nice into this, this rack mount that is made by APC. Now APC is normally thought of as the little UPSs that are under everyone's desk that power them when the power's out. But they make this nice rack. It comes in a 24 position as well as this 4 position. We modify it. We put a DIN rail connector on the back of it. But you can buy the big ones from Amazon at a really reasonable price. And if you want to feed power up a bunch of Ethernet cables from a NOC or any place that's rack mounted or perhaps a Hoffman box on the side of a tower, this is a really good way of going. If you really need to just go single circuit outside on the side of a building's wall, this is the way to go. Same circuit in both. Everything's the same except for the form factor. So I'm going to get in a little bit about these things, both surge suppressors and POE insertion or extraction. And let me grab the one that actually has the markings on it, the production markings. So this top jack is the Ethernet connection that has both data and power. Bottom jack is data only, and then here's power. Now the power is not all that important as far as the polarity goes. It's just light some LEDs up here is all. So we put the plus and minus on there just so that people could refer to the plus and minus side of the jack. You could say left, right, it doesn't really matter. The main thing you need to know about POE is that in GigE applications, I'm not talking about the older products where you'd put power on pairs, say 4, 5, 7, and 8, and no data flowed over them. That was a sub 100 megabit per second POE scenario and is used in a lot of internet wireless radio products like the original Cambium or Motorola, I should say, Motorola Canopy FSK 100 series and the original Ubiquity nano stations, for example. Those only had data on 1, 2, 3, and 6. Power ran over 4, 5, 7, and 8. I make a whole line of surge suppressors for those products as well. And you can say they're POE. But we're talking here is GigE POE. It's gig data on all 8 wires, and it can have power on all 8 wires. And the difference between my products and a lot of the POE products out there for GigE is that I make it programmable where you can put whatever polarity you want on whichever data wire you want. You can make all 8 wires positive if you want. There is one radio that needs all 8 wires to be positive, and the ground return comes back to the radio via the chassis ground. So presumably a ground wire hooked to the radio, or God forbid they're relying on the tower and the mount to do this, but crazier things have happened. But this makes it possible to really mix and match, customize, do whatever you want. And it also makes it to where you can put a lot more current over a POE circuit than you normally would. So I'm going to talk a little bit about the magic to blend the data and the power. In order to blend data and power, you've really only got 2 choices. You've got a wire, and it's got some kind of data on it, something analogous to an AC signal, okay? And you want to mix a DC signal in with that. About the only 2 choices you've got is you can put the AC on the wire through a capacitor, and you can inject the DC through a choke coil, and I'll show you what that circuit looks like, even though it has nothing to do with what we're talking about here today. There's the capacitor. Nice thing about capacitors is AC will go through them. And then on this side over here is you have an inductor, and maybe you inject some current. I'm going with conventional current flow here. All of you purists that want to talk about electron flow, just plug your ears. Positive is going to have the current coming out of it. Okay, so on the wire here you have both DC and you have AC. This is a very common circuit used in like satellite TV, you know, so you can run current up the coax and power whatsoever up there. Now I've never experimented around with it or not, but and that's usually an unbalanced circuit. I think in Ethernet you might get away with, like on pins 1 and 2, for example, you might get away with doing this and tying those both together and doing the opposite at the far end to block, DC blocking capacitors. I've never tried it to see if you could get GigE to go through something like that. It might actually work, and it really could save some money for a manufacturer. But it's not really the best way of doing it. Let me talk about, for a minute, transformer technology and how this idea of blending the AC and the DC onto the same wires goes way back. Goes 125 years back or so. All right, transformers. Okay, if you have a coil of wire, and it's going to be represented like this, schematically, and you put a changing current, okay? You can't just hook it up to a battery, but it has to, the current has to come and go, start and stop, change in intensity. What happens is, even if a DC, if you don't change it, you're going to be creating a magnetic field through those windings of that wire. But the interesting thing is, if you put another coil of wire close to that one, and you change the current on this side, strong, weak, on, off, you get the exact same, let's say it's a sine wave, you get the exact same thing over here. It converts the current to the magnetism. Magnetism goes through this coil and converts it back to current. Basic transformer theory. If you change the different number of windings on each side, you can actually jack the voltage up and down. Or another way of saying it is you can change the impedance. The impedance in is different than the impedance out. Normally, high impedance means high voltage. Low impedance means low voltage. But it's the opposite for the current. Low impedance means high current, like high amps, high milliamps, high microamps. What we have done over the years with transformers is typically converted high voltage out on a power pole down to something that your house appliances could use and much safer, but also it's been used quite extensively in the telephone industry for more than 100 years. What they originally did was the old carbon microphones in the old original telephones. Here, why don't you pan over here and take a look at this. That one doesn't even have it in it. I must have robbed it when I was a kid for some experiment. But these carbon microphones were really low impedance. It means it took a lot of, oh, here we go. Yeah, this is actually the phone I had as a kid prior to 1964. These old carbon microphone elements needed a lot of current. You'd have batteries in the phone, and it would run quite a bit of current through the carbon microphone to pick up the sound. But then out on the phone lines, you wanted to go a long distance with that voice. And in order to go a long distance on wires, normally you don't want high current, you want high voltage. So the phones had a transformer in them to convert that low impedance of the microphone, okay? You had this carbon microphone with carbon granules in it and actually hooked to a battery that's actually in the phone itself or connected to the phone. And then that was hooked to a transformer that was much higher impedance to go down the line and much higher voltage, a lot less current, but it would travel a long ways, get clear back to the central office. And in the early days, they didn't have amplifiers. And so that would then be bridged onto a line that might have went to the next town over on a trunk line. And it kept getting weaker and weaker and weaker every step of the way. They actually did some crazy old amps where they had a loudspeaker coupled acoustically to a microphone, and it would actually jack it up a little bit. But thank goodness Edison and Lee DeForest gave us amplifiers. So I'm digressing a long ways here from surge suppressors, but it all ties in, okay? Somebody at some point, and this actually goes back, I think, more to the telegraph era than it does the telephone era, but I'm not sure about that. Somebody discovered the fact that you could take a transformer, okay, and you could center tap it. All right, this is commonly used in the power poles. You've got 240 here and you've got 110 here. But it works also for our industry. And what they found is that you've got this varying AC or time varying digital up and down type of signal that's transferring across. But if you put a current in, I've got this drawn actually backwards. Let me take a break here. I'm going to erase this. I'm going to start the schematic over. All right, so I got a little better schematic here. So let's say we're going a distance here. We've got 3 circuits wires. We've got our AC, which I'm going to represent with blue, or our time varying DC signal. It could be a data circuit, you know, Ethernet that's going like this, but it must have an average value of 0 in order to work for a transformer. Okay, that's really the most important part. Now, it gets transferred over here too, going both ways, all the way through this whole circuit. But what somebody had the bright idea of once, quite some time ago, is they could insert another current into these center taps. And so this current would come up here and it would divide. It'd come up here and it'd turn around and go that way, and it would turn around and go that way, and then it would combine back at the center tap on the other end. The interesting thing is the magnetic fields that are being made by the current in this half of the winding are offset by the magnetic fields in this half of the winding, because the current goes up here and it splits. It goes that way and it goes that way. And so the direction of the current through the windings is what determines the north-south, and there's the right-hand rule and all of these rules, but all you have to know is the magnetic fields, if you've got two norths together, 2 souths together, they cancel out. There's no magnetic field there caused by this new current. Same thing is happening over here. And so the upshot of all of this is that the additional magnetic currents from this center tap circuit aren't causing a problem to this blue signal. Well, shouldn't be causing a problem. I'm going to get into transformer core saturation here in a little bit. So let me draw you a new schematic. Okay, so this is actually more representative of how this center tap scenario actually got used. In the phone industry, you know, you've got the AC, the voice, or the data, or whatever, flowing through this circuit. Okay, this is at your house, central office, next town over, whatever it happens to be. And then you've got a whole nother circuit down here. You're talking to your grandma here. Maybe here, the businessman is talking to the banker, and somebody says, hey, wouldn't it be a cool idea if we put a whole new circuit on these center taps? So here's both sides of the circuit, okay? And you could actually put AC on this center tap, and the AC signal or the voice or whatever we were putting on it on this circuit, it does this whole cancellation out thing in all of these transformers all the way down the line. So this doesn't mix. Assuming all of the windings on all of these transformers are identical in impedance and in resistance, the data or the voice just doesn't mix. This circuit right here in the middle is originally and historically called a phantom circuit. Phantom, I guess, because it doesn't actually exist. There's no wires out there on the pole, on the glass insulator. So they could take two circuits and make 3 out of it. Phantom circuit. This is exactly what we're doing with GigE POE. We're just running the power over the phantom circuit. And we've got 8 wires, so we can have 4 sets of this, and we can run a lot of power over it, relatively speaking. Let me get to that in just a second here. I apologize to those of you who like everything to be nice and plumb and square. I realize I'm a little bit crooked here, but this is the transformer that's used in the GigE POE product. It's a little more complicated than the things I was drawing up there before, but essentially this is still a transformer with a center tap. They've just kind of went out of their way to show that there's really 2 separate windings there. And there's more to it than just simple windings. These are kind of an extra bit of inductance in there that helps to balance things out on the line. These little black lines means there's actually some kind of a metallic core material, because you can get just 2 coils of wire next to each other in air and vacuum. They'll couple depending on the frequencies, but you want high efficiency, high coupling. You normally put some kind of core material between the 2 coils of wire, like metal of some sort, like a ferrous metal, a steel, laminated steel, powdered iron, and I think in our case we're going to find that these are probably powdered iron transformers. So this is what you find in the products that I sell. These are made by a company called Pulse. I think it's Pulse Engineering or Pulse Electronics. They're recognized as one of the best magnetics for GigE that there is on the planet. There's a lot of knockoff stuff coming out of the Far East that uses inferior magnetics, and I'm going to get to that in a minute here. Here's a simplified schematic that I include in on the website for my products, and you can see where I didn't really include this part, but it's important here to notice what I've done here with jumpers and switches so you can select how you put the power in and power out. We're going to get a close-up of the device here in a minute, and I'll show you exactly how that works. But what I've essentially done is the data is coming and going here, and I've taken this center tap and I've given you some jumpers, some 3-pin jumpers, and I've made it to where you can jump it, either side of it, over to this input DC connector, this Phoenix connector on the side. So if you want all your center taps to be hooked to one of the screw terminals on that, you can do that. You can select that. So let's talk a little bit about core saturation. Sorry about the low quality of this particular shot. We taped it up here to the whiteboard. We added some light. Not much we can do. We don't have a macro adapter for the camera, so you're going to just have to put up with it. All of these little things in here are actually donuts. They're made out of a pressed metal. The manufacturers all have their own super secret recipes for their pressed metal. And it depends on the frequency that you're passing through it, and it depends on the use, whether it's a radio frequency device. But this is what makes or breaks the transformers that are used in POE products, GigE POE products. And I'll draw you a little bit larger diagram here on the whiteboard of what you're at. What I was attempting to show on another shot was these 8 toroidal transformers in here. This is one of them, and this is one of them, okay? So the actual POE transformer itself on an individual data circuit, like say pins 1 and 2, flows through actually 2 of these donut things. And let me draw you a picture of what's going on with the donuts. All right, so inside the donut is an actual donut. It's a toroid. It's compressed metal. It's smashed down in forms, and it's a powdered iron type of thing. And what you've got, if you're making a transformer, a toroidal transformer, you actually have to stitch those wires through it. And that's what you're seeing in this tiny little thing over here. This particular one, all of the wires are kind of copper colored. Some of them I've seen actually use a red and green dye on them so you can tell them apart. But in our case here, you'd have a couple of windings there. And the nice thing about toroids is they're self-shielding. All of the magnetic lines of force that goes through a toroid, that those coils of wire create these magnetic fields of force, they all stay self-contained within the toroid. So you can't put 2 toroids next to each other, and theoretically they shouldn't be picking up signal from each other. They're very nice in that respect. They're also a way of making a very, very tiny transformer. I've joked before that in the factory they have these tiny little monkeys, little capuchin monkeys, sewing these little pieces of wire in through these donuts. No idea how they do it. I'm sure it's some kind of a blindingly fast sewing machine type of device that does it. But this kind of, I think, I don't know if this is true, but I know that during the early days of computing, when they were trying to miniaturize things, especially for the Apollo program, they needed magnetic memory that was reliable, and they used magnetic core memory, and they actually literally did stitch the little toroids with the core memory. I don't know which came first, the magnetic cores or the little toroidal transformers. But that's what's going on inside them, and let me talk about why it's important that you have a good core in your product. All right, we're going to talk about the core just a minute. Go back to the original transformer or coil or solenoid. It's just some windings around something. Could be air, but normally you get a little stronger magnetic field if you wind it around something that has some magnetic characteristics. Let's talk about, let's say those are laminations of steel. Okay, that's commonly used in power transformers. And when a time-varying signal goes through there, you're going to get a time-varying magnetic field generated. You know, it'll be north and south, and then when the sine wave flips over, you'll have south and then north. in the case of if it's plugged into the wall or something like that. Now, you keep cranking up the current in the windings, the magnetic field gets stronger and stronger and stronger up to a certain point, and then all of the little domains in the magnetic core, they're all being used up. You just can't make the magnetic field stronger by increasing the current, and that's called magnetic core saturation. Now, it's really important because you want that time varying magnetic field that's generated by the time varying data or voice or whatever the circuit is that it's hooked to. And in our case, it's gigabit Ethernet. And so you don't want a pulse coming along from a computer trying to excite a magnetic field in a core, but the core's all out of domains. It can't make it, and so it won't transfer that pulse. So magnetic core saturation is really important, and you don't want that to happen. Now, on an inferior PoE inserter where they're trying to scrimp by and use as little powdered metal as they can in their cores, you'll get core saturation at lower points. And why this is important, let me draw you that center tap transformer thing again. Okay, getting kind of back to where we started here. You've got Ethernet signal here. It's not truly a sine wave. It's got a lot of little, depends on the types of modulations. There's a half a dozen different ways Ethernet can be put on the wire. But over time, they generally look like some kind of an AC waveform. And you got that faithfully coming out over here, going on to whatever the device is. And then I come along and I say, well, maybe that device is a radio, okay? It's going up the pole to a radio with a nice antenna on it. And up here at the pole, I've got another transformer with a center tap. And I want to stick some juice in there and have it come out and feed back in to power the radio. Okay, that's a very simplified, very common thing, PoE. What happens though is if you start putting more and more and more current in there to power your radio, once you get up to the saturation level, all of a sudden this nice faithful Ethernet signal that's on this one side just starts looking like garbage. You're going to have Ethernet errors and eventually it's going to stop working altogether. So you can only put so much PoE current on these circuits. All right, let's talk a little bit about how much current you can actually put on that PoE circuit. The nice thing about pulses, they're very conservative. They say that you can put up to 350 milliamps per pair of wires, okay? So that would give you 12, 1.2, 1.3, 1.4 amps, if I did my mental arithmetic here correctly. What I've done though is I've fired these things up and I put a load on them and I just kept cranking up the current and cranking up the current and cranking up the current while having GigE test equipment on the circuit. I never did see the GigE get any Ethernet errors, but I did see this pulse transformer getting hot enough to actually unsolder itself from the board. Okay, I ran these for days and days and days under elevated temperatures, and I can tell you that the spec that I quote, you can be safe at running it at that. It is a little bit higher than the data sheet spec, but it works, and I guarantee it to work. Okay, let's talk a little bit about the flexibility of my products. On the back, you see a nice little diagram showing about these jumpers, these pin jumpers that are on the front. Okay, you pluck them off. If you're old enough, you'll remember plucking jumpers off of hard drives a long time ago to set up which A, B, C, or D or hard drive. Anyway, these pin jumpers help you to figure out which center tap is hooked to which of these two powering wires. Again, that polarity is not that important. You can just use it as a reference. I think if you hook it up as I've shown, the green light comes on, and if you hook it up backwards, the red light comes on. But on the back side here, you'll see that, and this represents the actual physical layout of the front side. Pairs 1 and 2, or of the Ethernet circuit, pairs 1 and 2 are programmed with this jumper, and you can direct the power that's on pair 1 and 2 to the positive terminal or the negative terminal, again referring here, so it's left. So if you put the jumper on the left, your choices here are left or right, the power is connected to the left. If you slide them over to the right two pins, that center tap is hooked to the right. If you put them all on the left, That means all PoE circuits go to the left and nothing is hooked to the right one. That's in that odd radio that uses all 8 wires to power the radio. So if you really want to get, you know, amp and a quarter, amp and a half up the tower at 48 volts, this will do it for you. A lot of PoE inserters that you buy, especially the low-cost ones that you find on the internet, they only put the power on 2 of the data circuits, not all 4. And so you only get half the amount of current that you can pump up to the device, and that's one way of saving money. If you're not putting power on all 8 wires, you can scrimp on the type of magnetics that you use inside it. It's important to note the top jack has blended data and power. The bottom jack is just data only. On the outdoor version, you've got the exact same thing. You got programming jumpers, you've got left and right power terminals. Those are the blue terminals in there. This one has the pluggable Phoenix type of connector to where you can wire up the PoE separately and then just plug it in later. It's kind of nice, a nice feature, but there really wasn't enough room in here to get that in there, get a ground lug in there, get the jacks in there. It just wouldn't have fit. So that's what we've got. Now I want to point out one more thing that's really important about these 2 products. Another aspect that we haven't talked about yet too much is the surge suppression. We make a lot of surge suppressors, and this particular one has a bunch of solid state devices here that are very quick in acting. Their spec sheet actually says they fire down in the picosecond range, but if you know anything about the math required to convert that into frequency, yeah, a picosecond pulse isn't going to go very far on these wires of these traces. They're going to have so much inductance, they're going to choke it out. But I'm sure the test factory, their special microwave test instrument to test them, it really does fire that fast. But they're really fast. They clip all kinds of stuff really, really fast. But they will explode and launch themselves off the board if you get too much current through them. And that's what surge suppressors are designed to do. I really want to enforce this point. These things are sacrificial devices. They take the bullet for your equipment, okay? So the fact that one of these things explodes off the wall and you send me a photograph of it saying, is this right? I generally write back and say, well, is the radio still working? And I get an answer, well, yeah, the radio's still working. So I guess, yes, this is right, in fact. Got some really interesting photos. But what we do here is to back up that super, super fast solid state device is these little devices right here. Those are called gas tube or gas discharge tube surge suppressors. They're nothing more than really what you can see here. There's 3 metal plates, and there's 2 ceramic insulators between the metal plates. The end metal plates are hooked up to the aggregate total. I mean, I've got steering circuitry on these things that funnel all of the surges down to the gas tube. So they funnel all the surges down to the 2 ends of the gas tube surge suppressor, and the middle of the gas tube discharge device is connected to the ground lug. And in this case, the middle of it's connected to the ground tab. As you can see, the APC devices have a really thick grounding tab, and it connects to a long grounding circuit inside the case. So how does that work? How does a gas tube actually do any good? I mean, it's just 2 metal plates with some ceramic insulators. Well, the magic is in the gas. There is a gas inside here. It's not air, it's not vacuum. It's going to be a neon or an argon or a blend, maybe a little carbon dioxide. There's various exotic blends. And all of those blends do is they set up a voltage, breakdown voltage. As a matter of fact, there were some older gas tubes that I think had tritium in them because they were all marked with that cool radioactive label on them. They were a black, shiny glass tube. I loved those things, I guess because it had the radioactive sticker on it. But in any event, if you put radioactivity in there, it'll actually make it break down at a lower voltage. What they're doing here is once the voltage gets up high enough in this gas, that the actual voltage strips the electrons off of the gas, and so you have free electrons in there, and of course free electrons are what we all need to conduct electricity. And that's the firing point or the breakdown point of the gas. Same way fluorescent lights work. And once you have a lot of free electrons in there, this thing basically just becomes a dead short circuit to ground. So all of these surges that we funneled through all of these steering devices to these ends, once these gas tubes fired, you're just shorting it to ground, and that's where you want your impulse to go, is to ground. These things will take multiple hits. Nobody will say how many, because every hit's different. Different current, different voltage, but they do survive. When they fire off in the lab, you see this nice pink glow coming from them. I have my surge simulator is current limited because I don't really want to launch any components off of the face of the circuit board by doing a destructive test on these things. Okay, now on this one you see the POE, the blended data and the power is on this jack, and this jack is just data only. We give you a little bit of cheat sheet here in this one. Data only, data and POE. The label in here also gives you a little bit more information. There's just not a lot of room here on this circuit board to give you a whole lot of information. But hopefully if you have some questions, you can come back to this video and I'll refresh your memory. If you also notice this device right here, this is a secondary solid state discharge device. This one backs up these, and this backs up these. So you've actually got 3 levels of backup in this surge suppressor. So thanks for listening along. I get pedantic. It's my Mr. Wizard coming out, but you know, my jacket says Animal Farm on it. Animal Farm's our trade show where we invite manufacturers to come and talk about their products. It's kind of the untrade show in that it's not a sales pitch. But a lot of you already know me, Chuck McCown, McCown Technology Corporation. I manufacture these products, I stand behind these products, and all of these products have come from guys like you that want something different. And you write me a letter or talk to me on the phone and say, hey, I could really use a dot, 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 dot. I run through 2 or 3 iterations and voila, a new product is born. So that's the best products. The ones I invent all on my own, say, boy, this is really neat. Nobody ever buys those things. So let me know what you need. Let me know how I can make these videos better. I'm certainly not a video guy. And I don't want to get sued by Tom Dixon of Will It Blend either. So I'm not gonna use any funky will it bend, will it blow, will it anything. Tom, hi, appreciate you.